Okay, well, let me go ahead and get started here. We have a fair amount to cover. So today we're going to talk about power analysis and sample size estimation. And there's a number of topics that we want to cover here. So I'm going to do a little bit of review of statistical decision-making, what we mean by statistical power and how we estimate sample size. And then talk about specific calculations for linear models, time to event analyses, and then just a couple of comments on testing for equivalence or non-inferiority, and then sequential analyses and clustered data, and then spend a fair amount of time on the information that we would need to do a power analysis, and then end up by talking about abuse of power or a specific don't for power analysis. Okay, so when you plan a study, you're going to need to estimate how many patients or how many subjects you need. And the sample size is needed to demonstrate that the result is not likely due to random sampling variability or chance. And the primary thing that we're interested in is the effect size or the effect. And that's the difference in whatever your statistics means, proportions, odd ratios, and so on, between your comparison groups. Effect and effect size, I'm using those kind of interchangeably. Technically, they have different meanings, but that's not strictly important. And so how do you determine the effect size? Well, there's different ways of doing that. Sometimes it's based on clinical experience or consensus among clinicians. You can use prior published studies to get an idea of the effect that you want to be able to demonstrate. Or often a pilot or feasibility study is done to get an estimate. If you have absolutely no idea, then what we can do, or a statistician can do, is give you kind of best guess scenarios depending on the data that you have. So the considerations for sample size estimation, of course, we would need to know your research design and the statistical analysis that you would do as a result of that. If you have a randomized trial, that's pretty straightforward. If you have a non-randomized study, then there's potentially confounding covariates that we may need to account for. And then regardless of whether it's randomized or not, there might be interactions among variables or subgroup analyses. And typically those require larger sample size than just a straight up comparison of groups, how 2 or 3 or 4 groups. And then also it may be that your study wants to do some interim analyses. And so that requires an additional computation for sample size. So let me review a little bit here of hypothesis testing. Our research hypothesis is, of course, a statement that we believe to be true about our population of interest. And quantitatively, this is stated as an effect, or as I mentioned before, the difference in means or difference in proportions between your treatment or therapy groups. The null hypothesis then is stated contrary to the research hypothesis. That is, it's the hypothesis that there is no difference. And the p-value that we get is the probability that the observed effect could have been obtained if the null hypothesis were true. Or we can say that it's the probability that the research results were due to random sampling error or chance. So the test statistic that we compute from our statistical test that we're going to do is compared then to the known distribution of what would be expected if the null hypothesis were true. And basically our test statistics is our observed value minus the hypothesized value, or the observed value in a, say, control group or placebo group, divided by the standard error of the difference. And in a sense, the numerator then is the effect that we're interested in, and the denominator is a measure of the variability of the sample statistics, sampling distribution. And as I think we've talked about before, sampling distributions are, for example, the normal distribution of the t-distribution, the chi-square distribution, and so on. And so those are the distributions that are our known distributions and what we expect if the null hypothesis is true. So when we reject the null hypothesis, basically what we're doing is we're trying to gain support for the research hypothesis. And if our p-value is small, then the probability that the effect occurred because of chance is small. What a p-value is not is the probability that the null hypothesis is true or that the research hypothesis is true. It's a conditional probability that the research results are due to chance if we assume the null hypothesis is true. And if the null hypothesis can be rejected, then we infer that the results that we get were due to something else other than random sampling error, primarily interested in our treatments or our therapies or whatever our intervention might be that we're interested in. If we can't reject the null hypothesis, and if our p-value is traditionally greater than 0.05, then all we can say is that there's no real evidence that the effect occurred as a result of anything other than chance. And it's not necessarily true that there is no real effect, because we don't know that for sure. Sometimes this is referred to as accepting the null hypothesis, but failure to reject is technically the correct way of not rejecting the null hypothesis. And so this is a diagram that I'm sure you've seen in many times in your statistical courses. And so if what we have represented is the rows are the conclusion that we get from our statistical test, and the columns are the true situation. So over here, if there's no real difference in the population, but based on our statistical test, we say that a difference exists, then we've made what's called a type 1 error, the probability being alpha, and this is the traditional 0.05 that you see in the literature. A type 2 error is when we conclude from our statistical test that there is no difference, that is, we fail to reject the null hypothesis, but in the population, there is a true difference. So we've made a type 2 error, and this probability is referred to as beta. And then the top left-hand cell here is what we're particularly interested in, because this is a correct decision. We assume or we conclude that there is a difference based on our statistical test, and there is a true difference in the population. And this probability is 1 minus beta, the type 2 error, and this is referred to as the power of our test. So if we reject the null hypothesis when it is indeed false, then there's always the possibility that we made a wrong decision. That is, we shouldn't have rejected the null hypothesis. And this is our type 1 error rate, or the p-value. But as far as power is concerned, we can increase it a couple of different ways. We can increase it by increasing the type 1 error rate, but that's not usually done because you don't want to reject the null hypothesis. You want to do your test in favor of having the type 1 error rate as small as possible. But another way, and the way that it's typically done, is that we can increase power by increasing the sample size. And so let me sort of illustrate this by looking at the null distribution, the distribution in red here. So that's our null hypothesis. And our alternative distribution, that's our hypothesis that we want to demonstrate. And so if we're using a t-distribution here, or we could be a chi-square distribution or a normal distribution, but the null distribution is referred to as a central t-distribution, and that's the distribution that is known if the null hypothesis is true. The distribution in blue is our alternative distribution. This is referred to as the non-central t-distribution. And so what we want to do here is to get sort of a trade-off here, or get a trade-off between the alpha error rate and the beta error rate, or the alpha error rate and power. And so our alpha error rate, or type 1 error rate, is represented by this part of the distribution of our null distribution, or our central distribution. And so this is typically the 0.05 or whatever you set your p-value level at. So that means that if the test statistic probability falls in this region of the null distribution, but we think it's actually part of the alternative distribution, then we've committed a type 1 error. This part of the alternative distribution is the beta error. So in other words, if we conclude that, or we think that our test statistic shows that our value, or our difference in our effects, falls in this part of the alternative distribution, but in fact it's actually part of the null distribution, and we've made a type 2 error. This part of the alternative distribution, then, that's to the right of my vertical line here, that's the power. In other words, that's 1 minus the beta error. So this represents the power of our statistical test. So let me give an example here of just doing a t-test for independent groups. And so we have two means, 85 in group 1 and 80 in group 2, with a standard deviation of 12 in each group. And so S sub x represents our common standard deviation, which is equal to the standard deviation of one of the other groups, since it's the same in this case, times the square root of the reciprocals of the n. And so let's say that we have 10 in each group. And so if we solve for our standard deviation of the difference, that's 12 times the square root of 1 over 10 plus 1 over 10, and that turns out to be about 5.4. And so our non-central distribution is just the difference in means divided by the standard deviation of the difference. So that's 5 divided by 5.4, essentially. And so we get, in our non-central distribution, a value of 0.93. So that's to the, that's our beta error rate. And so if we are looking, say, at the standard normal distribution here, remember that we've got 2.5% in each tail. So that's doing what we call a two-sided test. If it's just a one-sided test, then the entire 5% is in one or the other ends of the distribution. The t distribution is dependent on sample size, and it depends on quantity we call degrees of freedom, which is based on the sample size. But as the sample size gets large, then all of these sampling distributions, the t, the chi-square, the f, et cetera, tend to become a normal distribution, which is represented here by the thicker line where we have an infinite number of degrees of freedom, or an infinite sample size. So if we look at, in this case, in the non-central t distribution, so remember we had 10 in each group, so our degrees of freedom is n-1 plus n2 minus 1, or 9 plus 9, or 18. And as I mentioned, so if we're going to do a one-sided test, we'll just look at one end of the distribution. If we're going to do a two-sided test, then we would look at both ends of the distribution. So for a two-sided test with a p-value of 0.05 or alpha error rate of 0.05, we've got 0.025 in each tail. And so with 18 degrees of freedom, our t-value is 2.1. Or if we're doing a one-sided, or not a one-sided test, but if we're looking at the other direction, it could be a minus 2.1. So now, then, calculating from our beta distribution, we have 18 degrees of freedom. The t-value is 2.1, and so it turns out that our beta error is 0.86. And so then our power is 1 minus that, which in this case is 14%, 0.14 or 14%. So this is pretty low power. So how would we be able to increase power? Well, we increase it by increasing the sample size. And so let's say now that we have 100 per group, or 200 total. So now our standard deviation of the difference is 1.7. We take a difference in means, which we get 5, divided by 1.7, which is equal to 1.97. Now we have degrees of freedom. That's 100 minus 1 plus 100 minus 1, or 198. So now our beta, our probability of making a type 2 error, is essentially 0.17, and 1 minus that is 0.83, or 83% power. So now we've dramatically increased the power of our test by increasing the sample size. So this is the primary way, in fact, probably the only way that people increase power is by increasing the sample size in your study. So let me go through just some formulas here to show you what's involved, or what information that we need And so here's the calculation for a t-test, independent groups for two-sided. So in the numerator, we have 2 times sigma squared. Sigma is a standard deviation, the within group standard deviation. So if you just square that, you get the variance. And then we multiply that by our cutoffs, probabilities in the central distribution and in the non-central distribution. So in this case, I'm using the normal distribution of Z with alpha over 2. So I'm doing a two-sided test. So if we want to do our test at the 0.05 level, then that's 0.05 divided by 2, or it turns out that that's a normal distribution value of 1.96, or essentially 2. Then the normal sub beta, or the Z sub beta, that's the beta error rate. And so for, say, and what's typically used is a beta error rate of 0.2, which in the non-central distribution is 0.84, and that would give us power equal to 80%. And then the denominator delta is the effect, and that's squared. So if we have our information that we want to calculate our sample size, this is the way that we would calculate it. And the n is, say, if we have just, in this case with a t-test, just 2 groups, the n is for 1 group. So whatever we get, we'd have to multiply by 2 for 2 groups with equal sample sizes. If we have paired data or repeated measures data, then it's a similar sort of calculation, except that now we have some additional information that we need. And the one piece that we need is rho, the correlation between the paired measurements. And then we also need the number of repeated measurements. So if it's just a paired t-test, that would just be 2. The S squared is the variance of the correlated data. And then the delta, again, is our effect that we want to be able to demonstrate. So it's the same kind of idea here, but we need a few additional parameters to calculate. If we have analysis of covariance, that is, we have, say we want to look at 2 intervention groups, but we have, say, for example, in an non-randomized study, there might be some covariates that would influence the outcome. So we want to include those in the analysis. So we have to take in the correlation then between the outcome and the covariate. And so we calculate this just like we would for a t-test, or we could have more than 2 groups here. But what we then need to do is whatever number we get, we need to multiply that by 1 minus the correlation. So if the correlation is 0.2, then we multiply the n by 0.8. And it turns out that the smaller the correlation, then the larger sample size that's going to be needed. So if we have independent proportions, so this would be, for example, if we had 2 proportions we wanted to compare, and we're just going to use a chi-square test, or independent groups using the normal distribution. What we need here is we have our cutoffs for our alpha error rate and our beta error rate. But then we take this time the variance of the two groups. And so where P1 is the proportion that we believe is going to be characteristic of group 1, and P2 is the correlation of, not the correlation, the proportion in group 2. And so P times 1 minus P is the variance of a proportion. You take the square root of that and you get the standard deviation of a proportion. The denominator is epsilon minus delta, and then we square that, where epsilon is the expected difference in proportions. Usually we set this to 0 as our null hypothesis, as we're going to assume that there's no difference. And then delta is our superiority margin, or the difference that we think we would like to see. And then the other one that I want to look at is for time to event data, in particular, doing like Cox proportional hazards regression. So in this case, again, our numerator is as before. The denominator then is a little bit different, where P1 and P2 are the proportions in group 1 and proportion in group 2, and D is the expected failure rate in the entire sample, or how many are going to say die in our study or experience hospital readmission, or whatever the failure rate is. And then B is the hazard rate. And so this is the part of the formula here that we can vary depending on how big of an effect we want to see. And so the log of beta, the hazard rate, is just an odds ratio, or not an odds ratio, but a hazard ratio. So we can plug in here how big of a hazard ratio we would want to see. So if, a hazard ratio of 1 means that there's no difference. So do we want to see a hazard ratio of 1.2, 1.5, of 2? So that's what we would put in that part of the numerator. Or depending on how we look at the two groups we have, we can put in a hazard ratio of less than 1, 0.75, 0.5. That just depends on which way you subtract the difference. Okay, so that's just a few examples. There are others that are get more complicated than that. I want to talk a little bit about equivalence and non-inferiority. So equivalence is the hypothesis that there is no difference between groups. And so a lot of people think, well, if you fail to reject the null hypothesis, haven't you shown equivalence? Well, no, you haven't. As we pointed out before, all you can say is we have no evidence of a difference. But if you actually want to show equivalence or non-inferiority, that is, so for example, that a treatment group is no worse than a standard of care or a placebo group, then what we need to do is we need to specify a margin of equivalence or a margin of non-inferiority. And so for equivalence, means that we could have a value that's lower than the expected value or higher than the expected value. So for example, if we are looking at a margin where we'll call it equivalence if it falls within 10% of our observed value, then that means that we would have 5% on either side. In other words, it'd be plus or minus 5%. A margin of inferiority is always on the negative side. In other words, what you want to show is that the the treatment or your intervention group is no worse, but you've got to specify what worse means, or how big of a difference are you willing to tolerate, and then say that it's no worse than the standard of care. So generally, you need a larger N to demonstrate equivalence rather than superiority or non-inferiority. And then obviously you would guess that the smaller the margin, then the larger the N you're going to need. So if we have, say 10%, but our margin is only say 2.5%, then that's going to require a larger number of patients. Group sequential designs are where we want to take more than one look at the data or do more than one analysis. And so what we do in this case is calculate what our alpha error spending function would look like. And so generally for the first analysis, or for the first look at the data, the alpha error rate is really small. So for example, we might have 0.001 for our statistical significance on our first analysis, then at our second analysis would be 0.049. It's not calculated that simply, but that's the basic idea. And so then we can calculate stopping rules where we, in this case, say we're going to take 4 different looks at the data. Here is our initial one, our second one, our third one, and then our last one is going to be our 4th look at the data. And so we can calculate these boundaries where at each look, we can either continue the study, or if it falls outside of our boundaries here, then we'll either reject the null hypothesis or we'll accept the null hypothesis. And so, for example, here, if on our 3rd look we find statistical significance, then we could stop the study. On the other hand, if it looks like the tests look like this at the 3rd study, then there's no possibility that we're going to be able to accept or reject the null hypothesis. So again, we could stop the study on the basis of futility. This is done particularly in large trials where cost of doing the study is really important to consider. And then finally, cluster randomized designs, where our cluster is the unit of analysis. We have data from individual subjects, but a group of patients or subjects has come from, say, different hospitals or has different providers. And so power in this case is dependent on the number of clusters and the cluster size, as well as the correlation between clusters. So you have several things to consider if you're doing a cluster design. Okay, so the information that we need for a sample size estimation, of course, we need to know what the study design, what our research hypothesis is. We need to know the type 1 error rate, which is in most studies 0.05. And then the other thing that we need to know as far as error rates is the type 2 error rate, or the beta error rate. And so typically, this is what is not so much standardized. But a lot of times you'll see the beta error rate of 0.2, which gives us 80% power, but often the error rate of 0.15 or 0.1, where we have 85% and 90% power, are often calculated. And so, and then we need to know the effect, that is the difference in means or proportions or whatever the statistic is. And then we need to know the variance of the difference, or if you have a standard deviation of the difference, then we can obviously calculate the variance. If we have correlated data or paired data, then we need to know the correlation. The larger the correlation, the smaller the sample size, and vice versa. And oftentimes this is a real unknown because you are not real sure. And so often if I calculate this, I'll take a correlation of 0.2, which is a little on the small side, which would give you a larger number of subjects or patients that you would need. If we're doing a time to event analysis, then we need to know the time that people are enrolled, how long they're followed up for, obviously the overall event rate that would be expected. And then also if there's a possibility of crossing over, say from one treatment to another, we'd need to know what that is. And then we would also need to know the dropout rate. Actually, we need to know the dropout rate for all of the different analyses that we would do. And dropout rate meaning, patients drop out for one reason or another that may or may not be related to the intervention. So how do it's an easy calculation to determine how many patients we need, assuming a particular dropout rate. And so it's just the total number we would need is just the number calculated from our power analysis divided by 1 minus the dropout rate. And so, for example, if we calculated that we needed 200 patients in a study and we expected a 20% dropout rate, then that's 200 divided by 0.8 or 250. If we expect a 30% dropout rate, then we're going to need more, obviously. So that's 200 divided by 0.7 or 286. So that's how you calculate sample size, factoring in a dropout rate. Okay, so I want to give a couple of examples here to show you how this is done. So in this first example, we have a pilot study to assess whether drug A or drug B was more effective in lowering blood pressure at 1 month. And it was found that the decrease in systolic blood pressure was 11 millimeters of mercury for drug A and 8 for drug B. We're going to then calculate the standard deviation of the difference, which we'll assume is fairly large in this case, 10 millimeters of mercury. And then so our question, of course, is how many patients are we going to need in each group to demonstrate the difference of 3 millimeters of mercury with 80% power, an alpha rate of 5%, and we're going to allow for a 10% loss to follow up. And in doing this, we're going to assume that the loss is going to be equal in each group, which of course may or may not be true. So going back several slides I have the formula that we need here. So we have our within group standard deviation, which we said was 10. Oh, I think I got the wrong number in here, but that's okay. So we would have 2 times our standard deviation squared our variance, which I put 200 in here, but if it was 10, then it would be 100. And then we have our Z values for the normal distribution for the alpha error rate, which for 5% is 1.96 for a 2-sided error rate, is 1.96. And then for the beta error rate, 0.84. So we carry that out, and then our difference is 3. And so that's squared, and so that turns out to be 60 per group. I think I calculated that for a standard deviation of 10 and not, but anyway, as far as an example goes here, we would need then 120 total patients for this study, if in a larger study. And so if we calculate the number needed for 10% dropout, then that's just 120 divided by 0.9, or 133 total. If you have a number that turns out to have a decimal in it, regardless of what the decimal is, you always round up, even if it's like, well, I guess I usually don't round up if it's like less than 0.1, but if it's even if this was say 66.1 or 66.2, I'd round up to 67. So that then tells us that we need 67 per group, or we would have 134 total subjects in this study. Okay, in example 2, we're going to compare two treatments with respect to 30-day hospital readmission rates. And we want to demonstrate that treatment A will result in lower readmission rate by a factor of 10. This time we're going to calculate for 90% power. Since we've said that we think A is lower, we'll have a one-sided alpha error rate of 5%. And we're going to assume a dropout rate of 20%. And in this case, since we're doing a fairly short time between hospital discharge and readmission, we can just compare proportions here. If the outcome was longer, if follow-up was longer, say 1 or 2 years, then the Cox regression or time to event analysis would be more appropriate. But we can just compare the proportion readmitted within 30 days. So again, this is the formula that we had before for comparing proportions. And so remember, we have a one-sided error rate of 5%. So that value, that Z value is 1.64. And now since we have we want to do a 90% power, or the beta error rate is going to be 0.1, then that value in the non-central distribution is 1.28. And we're going to assume that the proportion in group 1 and group A is 0.3 that are readmitted, and in group 2 it's going to be 0.4. So that's basically a difference of 10%. And so we then multiply all that out and divide by, in this case, we set epsilon equal to 0 because we're assuming that the null hypothesis is true. And so our delta is 0.1. And so in this case, we get 384 per group, or 768 total. And so we're assuming now that we're going to have a 20% dropout. So that's 768 total divided by 0.8. So now we get 960 total, or 480 in a group. So you can see that in this case, our dropout rate is higher, and particularly for proportions here, that our sample size is quite large. Okay, and then finally, want to do a repeated measures study here. So we want to compare groups A and B with respect to change in SF-12 scores from baseline out to 1 year. And we want to assess whether the change in scores differs by 5 or more points between groups with 80% power and error rate of 5%. And we're going to allow for 10% loss to follow up. And the baseline scores are going to be obtained at, or the SF scores are going to be obtained at baseline, 1 month, 6 months, and 12 months. We're going to assume that the within group standard deviation is 10 scale points. The within subject variance, that is for the repeated measures, we're going to assume to be 2. And we'll assume a correlation of 0.2 across all repeated measures. In practice, in reality, that's not probably a very good assumption, because generally when you have repeated measures, the variance increases as you go further out in time. But for simplicity here, we'll just assume 0.2 correlation across all repeated measures. So our formula, as we looked at before, has these elements. So we plug these in. So we have 2 times 100, where that's our within group standard deviation is 10. 1.96 plus 0.84 as before, with a 2-sided alpha rate of 0.05 and beta error rate of 0.2. Then we have our correlation between the repeated measures, which is, we said, was 0.2, so that's 1 minus 0.2. And then we divide that by K, where K is the number of repeated measures. So we have 4 in this case. 2 is our within subject variance, or the variance due to repeated measures. And then we want to look at a difference of 5, that's our delta. So 4 times 2 times 5 squared. And you can see that this comes out to be a really small number, that we would only need 7 per group, or 14 total. And if we assume a 10% dropout, then the 14 basically only increases to 16, or 8 per group. And so this is really typical when you have repeated measures or paired data. You need generally fewer patients than you do if you don't have paired data, or the data come from independent groups without repeated measures. Now, I will say that if this was a real study that you wanted to do, you probably want to have more than 14 patients or subjects in your, or 16 in your study. So typically, if this would turn out to be what I actually got for a calculation, I would say, well, you know, with just 8 patients in a group, even if you find statistical significance, we're going to be kind of suspicious of that. So you probably should get a lot more. However many that would kind of depend upon you know, several factors, but we probably increase it to you know, at least more than 30 patients, or you know, even up to 100 patients. So this gives you an example of how we calculate our sample size based on the different parameters that go into these calculations. Okay, so finally, I want to talk about the concept of abusing power. And so one way that this is done is inflating the effect size. So oftentimes you'll see in actually studies that are published quite a large effect size. And you can kind of tell that they did this to get the sample size down to where probably to what they could afford. But when you look at the effect size, you want to have a meaningful or clinically important difference. Don't inflate the effect size just to reduce the number of patients you're going to need. Then also another way that you can abuse power is assuming a large correlation for paired data. So as the correlation gets large, if you assume, say, like a 0.75 correlation, then you're going to need a lot less patients than if the correlation was only 0.2. If we have repeated measure studies, as I mentioned before, typically the variance increases with time, and the correlation is not the same over the repeated measures. So there's a way we can, calculate that, but it's obviously a little more complicated. And then one thing that used to be done fairly commonly, but I don't know that it's so much true anymore, but you see people sometimes do a post hoc power analysis if you get non-significant results. And so what they want to say is that, well, if we'd had this many more subjects, we would have found significant results. But this doesn't have any meaning, and you can't say that adding subjects would have resulted in statistical significance, because you've already done the study, and adding, patients is going to change a lot of the parameters. So that's an improper use of a power analysis to do post hoc power analysis. What you can use your results for is to power another study or a future study. So the primary issue that's often or that's is true of sample size calculations is that it's turns out to be highly dependent on the cost and feasibility of getting patients or subject, because everybody has a limited budget. There's only, so much money, and so that means that there's only so many patients or subjects. So even though you might calculate, a sample size like we did for the one where we needed 900 patients, the investigator is going to say there's no way that we can afford that many. So we have to then do some sort of adjustment. And then the other issue is unknown parameters, particularly correlations, because it's really hard to know what the correlations, say, for example, of repeated measures or for analysis of covariance might be. And so that's often just an estimate or a guess. So we get an estimate of effect sizes from pilot studies. I would say that in a pilot study or a feasibility study, a power analysis isn't necessary. However, a lot of times people have asked me to do it anyway. And so we want to power on a meaningful or theoretical effect size, but put in text of the pilot study. And so for a pilot study, you should probably have 20 to 30 patients. And sometimes people say, if you get statistical significance in your pilot study, isn't the study over? Well, no, because statistical significance with small samples tends to be spurious. Because if you add more subject, you could get, a different result. So, and then the last thing I want to mention is if you have no idea what an effect size is, then we can do kind of a worst case, best case scenario, or give some ranges. So for example, if we have say 10% effect size, then depending on what our analysis is, then we would need, say, for 80, 85% and 90% power, 75, 115, and 240, subjects. If you had a bigger effect size, then obviously for those power levels, the number is going to be smaller. So in this case, then the investigator needs to think of he really need to think of a meaningful and a realistic number of patients that he or she can afford, and then go from there. So there's a ton of software that will do power analyses. The major statistical packages have them: SAS, State, SPSS. There's in R as well. Two specialty packages that are particularly popular are Inquiry and PASS. So obviously these are ones that you or somebody has to pay for. But if you can find money for them, they're certainly worth it. I particularly use the PASS software, but you can get, if you have a simple study like just a t-test or a paired t-test, you can probably go online and calculate that, given putting in the different parameters that are needed. And then I have just a few references here for sample size calculations, and then the article that talks about the abuse of power, and that's been around now for almost 25 years. And so I think that's probably why that's not a power analysis, a post hoc power analysis is not typically done anymore. Okay, so I will stop there as we're just about out of time. I want to thank you for your time and attention, and if there's any questions, you can email me at my email address here at MedStar, or are there any questions that in just a couple of minutes here that you might have using the Q&A? Okay, great. So if not, again, thank you for your time and attention. As I say, if you have, oh, here, okay, we have one. Oh, thanks. Thank you. Yeah. And let me mention that a recording of this, as well as the slides, are made available to those who are registered. So that should be sent to you in a couple of days from Georgetown. So again, thank you, and we'll see you next month.